Hey everyone, welcome to the third session of the ACS online webinar series. I'm Akshansh and this is Tirtha Senan. And today we're going to be handling, well, kind of one topic, but we're going to branch off into another topic. So I'll be taking up quantum physics today, just going over, basic stuff and introducing a slightly interesting thing. And Tirtha will be taking quantum computing because he loves quantum computing. So, let's get right into this. First off, I would like to quote one of my favorite physicists and possibly a lot of people's favorite physicist, Richard Feynman, who once said, "If you think you understand quantum physics, you don't understand quantum physics." And this line is quite misinterpreted quite often, but it actually has a far deeper meaning. And perhaps after this, session, you guys will understand. So I'll just go right into it. Quantum physics is basically used to describe the smallest of things in our universe, at the atomic or molecular, mostly the atomic level, say subatomic electrons, neutrons, protons, etc. And stuff doesn't quite work the same way at that small scale, when compared to our larger scale, which we use Newtonian mechanics and classical physics for that. So for quantum, in the quantum field, you have only subatomic particles and smaller. So rather than looking at things as particles, in quantum physics, we tend to look at them as waves. Because, well, first of all, waves are a lot more elegant. And when you come into quantum physics, you realize that everything is just, a function of probability and not exactly the way you think it would be. So the first thing that was conceived was a wave function. And a wave function was used to describe, any quantum object which which was small enough to be called a quantum object. But don't get mistaken, a wave function isn't exactly a physical function. It's like a mathematical function that's used to describe the state of a quantum object. And it's basically you evolve the wave function using Schrodinger's wave equation, which we've all learned, hopefully. And basically, if you want to locate a quantum object, you don't just look at it and locate it. In fact, what you're doing is, the way it works is, say you have an outcome for a quantum object, which is represented in its wave function. Then the amplitude of that outcome on the wave function, if you square that amplitude, what happens is you square all the amplitudes, you get a wave, which is completely positive. And this is called the probability distribution function, which I'm sure a lot of us have heard of psi square. So that's what that is. You take the amplitude of that certain outcome and you square it. So when you square it, you get the probability that at that point that object exists, that quantum object exists. So it's quite tough to grasp actually, but the thing is that this is how the real world out there is, and we're just starting to delve into these things, and it's a lot of fun, seriously. But coming back to classical physics, it went on the point that the universe was deterministic, and all the outcome of the universe could be completely determined based on knowledge of its current state and what's going on by using Newton's laws. So that's what classical physics said, but quantum physics said no, because quantum physics is cool. So you could actually picture this scenario. So say you had a quantum realm and you had our real world, which we observe. So in the quantum realm, everything is just waves. It's all wave functions of everything in the quantum realm. And in the real world, you have particles, which is what we observe, right? We don't just see waves when we look around. We see particles, we see things. So the barrier that's between this quantum realm and our own world is called a measurement barrier, and I will explain that. So basically, when you try to locate or say measures a certain quantity of a quantum object, you essentially collapse its wave function. So for you to be able to observe it, it has to exhibit a particle nature, and that happens when the wave function collapses and you see, a particle. So that is the scenario. So the measurement barrier basically is like, if I try to measure a quantum object state, I instantly collapse its wave function in such a way that the point or place where it was, based on the probability of that point in its wave function, I will see a certain outcome. So that is the measurement barrier, which is between the quantum realm and our real world. But there is a slight gap in our knowledge at this point, because you might ask, why does measurement have to collapse the wave function at all? I mean, why can't it just be, some other way of observing things? And this is where, well, we're still working on it. Science hasn't found the answer to this one yet. So measurement does collapse the wave function. We don't know why, but I'm sure we will in the near future. So, as I said, in classical physics, you have Newton's second law that helps you determine whatever will happen, like to say a body or a system over time. But in quantum physics, we have Schrodinger's wave equation, and the issue again is that you can't directly observe a wave function, right? So we can't just see waves and all. So you can't just directly plug in values into Schrodinger's wave equation if you want to observe something. So again, measurement collapses the wave function. That's our underlying thing for quantum mechanics as of now. So if you think about it, to us, like as humans and as scientists and as observers, the wave function really doesn't mean much to us because, well, we can't see it. We can't really interact much with it. All we can do is say that it exists in the quantum realm. And when we try to observe something, it collapses. So the measurement is technically more real than the wave function itself. So we should ideally be observing, we should be focusing on the measurements. But if say you're not observing the quantum object, then the wave function automatically evolves according to Schrodinger's wave equation. But when you are observing, you have a change, right? The wave function instantly collapses irreversibly, and you see the particle. So again, the probability of measuring a certain outcome with respect to a quantum object is given by the amplitude of the wave function of that outcome squared. So like this is kind of a weird idea because it's kind of saying if I observe something, then I use that probability equals square of amplitude thing. But when I don't observe the thing, we use Schrodinger's wave equation to develop it. And this kind of, it didn't sound very, true or right. So basically what Schrodinger, yes, Erwin Schrodinger, who we feel loves quantum mechanics, he didn't like this idea. He hated this idea. So this is when he came up with Schrodinger's cat. And I'm sure a lot of people have heard about Schrodinger's cat because it's quite a famous thought experiment. And just to brief you all about Schrodinger's cat, it has a box, an isolated box, inside which there's a cat. You put in a live cat, and you also have an atom, a radioactive atom, which should undergo decay or may not. It's a radioactive atom. And you also have a detector. So this detector is connected to a bottle of cyanide, like cyanide gas. And if the detector detects radiation coming from the decaying atom, it releases the gas. And if it releases the gas, obviously the cat dies. So one prerequisite here is the cat cannot interfere with the atom or the detector in any way. So if you think about it, the state, like whether the cat is dead or alive, the state of the cat is directly tied with the atom's decay and the detector, right? Because you have one state where the atom decays, the detector trips, and the cat dies. Or you have the other state where the atom doesn't decay, the detector doesn't trip, and the cat is alive. So these two states are there. And this is the beginning of the idea of quantum entanglement, which I will brief a bit more about later, and Tirtha will go into in detail. But yeah, that's the basics of that Schrodinger's cat, the experiment. But what quantum physics said was the atom doesn't have to decay or not decay. Like it's not a yes or no thing. Instead, quantum physics is trying to say that it exists in a superposition of both those states. So there is a certain probability that it will decay and a certain probability that it won't. But these states exist in superpositions, assuming that you don't measure. So again, the moment you measure, you collapse the wave function, right? So assuming you've made no measurements, it is always in a superposition of states. And that simply means that, well, we can't really comprehend that. I mean, how do you think of that? So that's like saying the cat is both dead and alive inside the box. But then once we open the box, it is only one of those. So this brings us to pretty much the foundations of quantum physics. And there's three aspects. Aspect number one is superposition, which basically is the idea that quantum objects can be in two different states at the same time. In fact, more than two. It could be any number. But the idea is quite fascinating, really. And I'm pretty sure you've all heard of the double slit experiment, Young's double slit experiment, quite famous. And that is pretty much the best depiction out there of superposition. And in the experiment, you fire electrons at a plate which has two tiny slits, and you have a screen behind it. And basically, what they did is initially just fired a random number of electrons, and they found an interference pattern at the back on the screen. And this meant that, well, if you can picture this, the two slits, if you have two slits, at each slit, if you have a wave, say a wave of, you can assume water, like if you have a wave of water coming at the slits, each opening of the slit becomes a new wave front. You have a new source, right? The wave starts to originate from there out. So you can picture, say, wave 1 and wave 2 expanding like this and interfering. So when these waves interfere, you have constructive interference at some points and destructive at others. So as they develop and evolve, what happens is the screen at the back, you have bright and dark, they're called fringes. So you have bright and dark fringes. So what people thought was, okay, I guess electrons, if you fire a bunch of electrons, maybe this could happen. Maybe it bounced off the slit and went like that. So scientists were very, confused and baffled, and they didn't want to give up just yet. So what they did was they took an electron firing machine, which could fire a single electron at a time. And now they said, okay, let's see what happens. So they fired one electron towards the sheet with two slits, and like by common sense, it either goes through the left slit or the right slit, right? So what they thought was, okay, we'll get a line here and a line here on the screen because of these two slits. But they observed the same interference pattern, the exact same pattern. After a while, they observed the exact same pattern, which meant each electron was going through both slits. I mean, does that make sense? Because scientists were damn confused. You have a single particle which is going. What is it interfering with? Like, it's the only particle there. What is it interfering with? How is it, forming the same interference pattern at the back? So then they said, okay, we'll place a detector. So they took a detector and they placed it at one of the slit openings. The moment they placed the detector there, they were like, okay, let's fire the electrons again. And as expected, the electrons went through 50% of the time from one slit and 50% of the time from the other. But the pattern observed at the back was not an interference pattern. It was two lines. As you would normally expect from a particle, it was two lines, like corresponding to the slits. And scientists were even more confused now because they were losing their minds. What is going on? How is it that I just put a detector there and the outcome of the experiment changed? So then they said, okay, we'll put the detector there, but we'll turn off the detector. So it's like a very cheeky way of saying that I'm going to see the electrons, but I'm not going to. Like, I'm just going to put the detector there and turn it off. So the electrons would feel like they're being watched, but they're not. They're like, yeah. So then again, they fired the electrons through one at a time, and they observed an interference pattern. So at this point, they were completely, they were mind blown because how is that possible? Because they were firing the same exact electrons one at a time. All they did was turn off the detector. And this brought them to the conclusion that if you observe or make a measurement upon a quantum object, the wave function, as in the wave nature or the probability of it being a wave, it simply collapses. It becomes a particle. So when the detector was on, you were observing the quantum object, and that's why you didn't observe the interference pattern. It behaved like a particle. But when you don't observe the quantum object, you do get an interference pattern. And that simply means that quantum objects always exist in a state of superposition until an observation or a measurement is made. So this was an absolutely beautiful experiment. I love this experiment. So yeah, that's superposition. Pretty not that tough to grasp, but tough to picture. So going on to the next one, we have entanglement. And entanglement is actually a really nice idea. So say you have, let's just take an example. We have two electrons and I fire them straight at each other with like equal and opposite velocities, right? So I just fire them like this and they bounce off, and their trajectories are given by, well, okay, let's say I'm not observing, I'm just firing them, right? So the trajectories are given by wave functions because each electron has its own wave function. And when they collide, the wave functions mix, right? So if you analyze a wave function, all you get is a probability, right? You don't just see the particle when you look like it analyze its wave function. So what people thought is, okay, we'll measure the momentum of one of the electrons after the collision, and automatically we know the other, right? This law of conservation of momentum, pretty easy, makes a lot of sense. So if you measure any one of them, you instantly collapse the wave function of the other. So you're able to influence the state of another quantum object just by observing one object. And that is what it meant to have a certain tie between them. So um, after the interactions, this is how quantum physics explained it. After the interactions, the electrons don't have separate wave functions. What happens is, so we've all studied about interference of waves, right? When two waves come together, right? So you have certain points of constructive and certain points of destructive interference and points in between. So what happens is, after collision, the electrons don't have separate wave functions. They have a single wave function, just one function. And that one wave function describes the entire state of the system, which is what it means to be entangled, right? If a particle is entangled with another, you can explain its behavior with respect to that one. So they share the same wave function after collision. And this brings us to quite an interesting idea, because that just means there's only ever one wave function, which is the wave function of the universe when it began, right? Because everything else has always been an outcome of that, or a reason, like a cause, an effect of that. So yeah, there's technically only one wave function, which is the wave function of the universe. But Einstein, well, he was not quite happy with this idea, simply because he had the theories of relativity, and they said that nothing can travel faster than light, no information can travel faster than light. But they observed, I mean, if you think about entanglement, I'm observing this one, and right after I observe this quantum object, the other quantum object has something done to it, and it knows that this something is being done to this because they're entangled. But that means that if even if that object is light years away, even if it's light years away and really far, if I observe this one, I instantly change the state of that one, and that one knows that this one has changed. But that would mean that information is being transmitted across them in a fraction of a second, regardless of how far they are. So Einstein, he would not believe this, obviously, because it's going against the fact that information shouldn't travel faster than speed of light. So he proposed a thought experiment, and he, say you take an event that it instantaneously affects, another event which is arbitrarily far away, because it's spooky. Like, how can something travel faster than light, right? That was his thought. So to explain this, he introduced the concept of quantum spin. Now, quantum spin is, well, it's not like implicit. It's not just spin, but it's kind of talking about angular momentum and spatial orientation, which are angular momentum is known to everyone. Spatial orientation just means an orientation of a particle or a quantum object in space. So that's what spin was trying to talk about. And so say you have two objects which are infinitely far away, not infinitely, let's just say really, really, really far away. And each of them has their own quantum spin, right? But if they're entangled, then by law of conservation of angular momentum, they should have opposite spins, right? That's what we feel. And then that would make sense, because if you measure one of them and you notice its spin is a certain quantity, you automatically know the other one, which would be an equal and opposite quantity, in order to cancel each other out, right? But the very interesting thing is, quantum physics is saying that the quantum spin of a quantum object is not defined. It's not well defined, at least. So you can't just say that a certain quantum object has some spin. Instead, it's in a superposition of different spin states. So that just means that until you even observe the first one spin, it's already in a superposition of states. Okay, and if this is in a superposition of states, so is the other one. So they're both in a superposition of spin states. So the moment you observe one of them, you collapse the wave function, which means the superposition gets broken, and you see only one outcome. And you instantly, the moment you see this outcome, you know the result of that one. So the moment you measure one of them, you know both of them, right? So it's almost as though the choice of your first measurement, it kind of influenced the result of the second. And that again is very, very interesting to think about, because how does that happen? So that's another thing that quantum physics is trying to say, that the speed of light isn't the limit for speed. But yeah, so that brings us to the last aspect of quantum physics, which is measurement. So as I'm continuously being saying throughout the stream, measurement collapses the wave function. I'll stop saying that. So yeah, it was weird that we had Schrodinger's equation for one, when we're not observing quantum objects, and then we had the probability equals amplitude squared thing for when we are observing quantum objects. So let's look at a bigger picture here. What is measurement really? I mean, like take Schrodinger's cat for example. You're opening the box, right? That's a way of measuring or obtaining information about what's in the box, right? If you think about it, the only way you're able to obtain information about what's in the box is if photons that hit the box or are in the box bounce off and come into your eyes, right? That's how you see things in the universe. So measurement is just the interaction of one quantum system with another. We are all quantum systems. I mean, we look macroscopic, but we're all made of the same, fundamental particles. So if measurement is just the interaction of two quantum systems, we already know how to deal with that, right? We just evolve each of their wave functions separately and see what happens. So that means that the moment we observe a quantum system and the moment we receive some sort of information from it, we ourselves get entangled with that quantum system. This is the fundamental basis of quantum entanglement. The moment you're trying to observe a quantum system, since you yourself are a quantum system, you get entangled with it. So like it's kind of mind-blowing, because that means that Schrodinger's cat is dead, but it's also alive, right? You're entangled with it. So for now, just to explain this a little bit clearer, let's check out all the rules that we have associated with measurement. So there's nothing, we're not talking about probability equals amplitude squared, nothing. Let's assume that measurement does not collapse the wave function. Let's just say that measurement is measurement, right? So you have the radioactive atom, you have which is in itself is in a superposition of both decayed and non-decayed states, and it's entangled with the detector, and obviously because of that it's entangled with the cat. So these three are already entangled inside, right? So the interesting way to think about it is the moment you start observing, what happens? You get entangled with all of that, right? So observation is just quantum entanglement. There is no collapse of the wave function. Again, this is just a theory, but I find this theory highly plausible. So observation just results in entanglement. There is nothing like the wave function collapses. The wave function is there. The wave function exists. It's only entangled with the wave functions of all the particles in you, your eyes and everything in the box, right? So this should mean that we see the cat as both dead and alive, right? But how is that possible? I mean, that makes no sense. You can't open a box and be like, oh, the cat is dead. No, it's dead. We don't know, right? So that really makes very less sense. So the theory that kind of supports all of these, or is supported by all of these, is that of parallel universes. And I'm not talking about the sci-fi parallel universe thing. I'm just talking about, parallel universes. I'll explain. So the version that you saw, like say you have two versions. One is the cat is dead when you open the box. The other is the cat is alive when you open the box, right? When you open the box, you're only going to see one of those. Before that, it's in a superposition and entangled. But once you open it, you'll only see one of those. So the idea here is each of those outcomes inhabits separate worlds. So not both of them are going to happen. They exist in their own complete realities, right? Those two states, dead and alive, never interact. Okay. So they exist in their own realities. And this brings us to a really interesting concept of, it's called environmental decoherence. And I'll explain that like now because it's very interesting. So inside the box, you have photons and photons whizzing around, right? So depending on whether the detector, releases cyanide gas or doesn't, the photons are going to bounce off in different ways, right? So the system of the detector plus atom is always, it's not always, but it is going to interact with the environment of the box itself, the air molecules and the photons and whatnot. So if it's going to interact with those, it's, entanglement again. So what happens is, since it's going to interact with in both states, like it's in the superposition of states itself. So what happens is the branch of the wave function of that combined system branches. And the branch is caused because of environmental influence. So this is called environmental decoherence, where you have a split in the wave function. So the wave function of the universe branches because both outcomes could have happened, but now they're branched apart, right? So now the air molecules and photons, they'll bounce off differently depending on the outcome, right? So you have an instant quantum entanglement followed like instantly by environmental decoherence, which is the splitting, the branching of the wave function. And this is called the many worlds interpretation. I'm sure a lot of you have heard about this many world interpretation of quantum mechanics, and it was proposed by Hugh Everett. So, yeah, amazing scientist. So this hypothesis, it actually clears up a lot of things, right? So now it just means that all we have are wave functions. We know how to evolve wave functions, Schrodinger's wave equation, and measurement doesn't really result in a collapse of the wave function, but it results in entanglement with a superposition of states. And what we experience is a small sliver of that, that multiverse of possibilities. So does that mean that all of them happen? Like, do all the outcomes happen 100% of the time? Because then the universe would be deterministic. But quantum physics was like, no, it's not. But now it's saying, yes, it is. So what's going on? I mean, how can all the outcomes happen all of the time? So again, this is one of those questions which has a very weird answer. But I like this interpretation of many worlds. So it's quite simple, really. Every time the universe, the wave function of the universe, it branches. What is happening is a quantum system in superposition gets entangled with another quantum system in superposition, right? Because say you're not observing them, they are in superposition. The moment they interact, they get entangled. Quantum entanglement is what happens. So the moment two systems in superposition get entangled with each other, you have a branch in the wave function. And when that happens, it doesn't exactly mean that all the outcomes are happening 100% of the time, but it does mean that the wave function obeys Schrodinger's equation, because Schrodinger's equation itself talks only about probabilities. So what happens is, if the branch, like if the wave function branches, it would make sense that we see only one outcome, but all the other outcomes are happening to us at the same time, but not us. It's different versions of us. So by versions, I don't necessarily mean physical entities, but it's different versions of us that have been branched off from our current wave function. We will never interact with them, although that version and us came from the same point. The moment you make an observation, you instantly branch, right? You branch, and because of the entanglement, it branches. And decoherence, environmental decoherence, as I said. And in each branch, one outcome's happening here, one outcome's happening here. You might have varying levels of the outcome based on the wave function because of different probabilities, but you're only going to experience one of them, right? And that's what people were trying to say when they said collapse the wave function. That's what they tried to say, that you'll only experience one outcome. But the many worlds interpretation says that you experience all of them, but not you. There's a lot of versions of you with each branch. So yeah, that's the idea of branching of the wave function. And again, this is just a theory and plausible theory, and it was made by us for our convenience to understand physics in our way. It's a decent interpretation, but again, there's so many different interpretations out there, like the Copenhagen interpretation and the von Neumann Wigner interpretation. You have a lot of them, but this is the interpretation that we perceived to be highly plausible. So yeah, the reason I brought the topic to parallel universes is because this is something that you can think about forever. Like, you can just keep thinking, because you can come up with your own theories and ideas, and it's a lot of fun. So just a reminder, all of this is hypothesis. Science is pretty much hypothesis based off of observation. So yeah, this is like an encouragement to explore a lot, and these are all just plausible theories that are worth discussing. So now I will stop ranting here, and I will hand it over to Tirtha, who will take up quantum computing. Over to you, Tirtha.
Hi. Yeah, thank you, Akshan. That was really very informative and probably a very good lead into the topic which I'm going to talk about. So, what I'm going to focus on is quantum computing. So, what is quantum computing? Some people might have heard something about this recently when Google and IBM were sharing some words. So, recently, what happened was Google had a quantum processor called Sycamore, which claimed to attain quantum supremacy. So, what is quantum supremacy? So, quantum supremacy was defined as when a quantum computer someday achieves this a speed which is faster than one of the fastest supercomputer or any supercomputer in this world. So Google claimed to have solved the problem by using its quantum computer in 200 seconds, while any supercomputer would, a state-of-the-art supercomputer would have taken 10,000 years. Like compare 10,000 years and 200 seconds. So that's a lot of difference. So they claim to attain quantum supremacy, but then IBM had stated that one of their supercomputers could like calculate and solve the problem in 2.5 days. But still, 2.5 days and 200 seconds have a lot of difference. So quantum computing is something that accelerates whatever computing we have, whatever equations or whatever problems you need to solve, it can do it in a faster speed. And why is that? And how does it do that? So I'll talk about that. So the basic principle of a conventional computer, like whatever computer you're viewing this through, this it may be your laptop, your PC, or your mobile phone. So all of this operates under bits. Probably we would have already known that ones and zeros. So how do these work is through transistors. So when an electrical voltage is detected, or simply saying one means on, zero means off. So this is what we have learned all this time, where one is on and zero is off, and then you can represent every decimal number and everything, converting into different numerical systems. So now, for example, let's take just one bit. So how can it exist? Zero or one. At a time, it can exist in zero or one. But in a quantum realm, whatever bit we are considering as, so these bits in a quantum realm are called qubits. In quantum computing, the bits are called qubits. So the main factor why this is really fast is it does not only exist as zero and one, but also 0 and 1 at the same time, as Akshan told, superposition. So there are different probabilities of 1 or 0, which would be for the qubit. So you may ask, what is this qubit? Like, for example, in classical computers, we have bits as, electrical on or off, like that, like when a voltage is there and not there. Qubits could be in many forms. It might be photons, and there are some semiconductors from which qubits are being developed to. They are researching much into it. Let's just stick to photons for now. So the thing which speeds it up is that it can exist in one or zero, and one and zero at the same time. So this speeds up the process exponentially. And how is that? So if you take let's take two bits. So in a normal computer, it can exist as zero and zero, or zero and one, or one and zero, or one and one, and all of these could be at only at one state. It can be either one of these four possibilities. But in a qubit, it can be anything out of these, or all of these. The probabilities are different for each state. So it can be 0 and 0, 0 and 1, 1 or 0, and 1 and 1 at the same moment, but with different probabilities. So this is what speeds up the process. So for example, if I have one normal bit, it can exist one of the four possibilities, but qubits can exist as all the four possibilities, which actually speeds up the process. For example, let's just take that you're storing the 26 alphabets of the English alphabets, so from A to Z, and you want to search for a specific key, like say K. So with normal bits, you might have to check one by one. So, but then in qubits, you can do it in a different way. So for 26 or 20, it doesn't make much difference. But when you go for big databases and you have lots of data, you can do it very efficiently. And quantum computing is also used to simulate a lot of things, just like supercomputers, where you simulate climate change, explosions, etc. Quantum computers will provide a whole new way to simulate these things. So before I go deep into how quantum computers work, I'll first talk a little about cryptography, how quantum computing is important in cryptography. So cryptography is very important, and it's very much linked to coding and decoding. And people who have seen this movie called Imitation Game, in which Benedict Cumberbatch acts, it's based on a real life story in which during World War II, the Germans used a coding system called Enigma to communicate with their forces. And it was very difficult to break this code. But then Alan Turing and his peers and his colleagues were able to make a machine called Turing machine, which had, which is one of the first ever computers and AI systems. Like people who learn AI now would be learning about Turing machines. So what it was able to do was to decode whatever the code was given. So cryptography and computer science, they're all very linked. So secure systems. Now we have a lot of cryptography. We have something called the PKC, which is the public key cryptography, and then we have RSA, which is one of the most famous cryptography system. And it's a lot of algorithms like this are being used today for crypto, like the encryption purposes. So now in the quantum realm, you might want to have a different way to communicate, because even the strongest algorithms like the RSA algorithm has been proven to be, like broken by quantum computers. It's still not much extensively, experimented. The reason being that you may need a lot of qubits to do that. For example, the some of the very strongest algorithms today, even if you put it into a supercomputer, it will take years and years, maybe thousands and so many years to decode it. But due to the quantum computing's special power, which is to exist in different states, it can crack it in a very much less time. So for example, for the RSA algorithm itself, there is an algorithm called Shor's algorithm. Many people might have heard about it. It was in the show Big Bang Theory too. So the Shor's algorithm, like it factors big, large numbers and decodes or like breaks the code, whatever encryption you're doing. So that is the kind of speed with which quantum computing can do that. So I'll just tell a short story where you can communicate in a quantum realm. I'll just share a screen over here. I hope I'm audible now. There were some technical issues. So, as I told, I'll just tell a short story about quantum cryptography over here. Share my screen. Yeah. Okay. So, the small story is going to be, before I go to that, I'll just talk about polarization, something which we would have learned in our 12th grade and would have learned in our college too. So, what is polarization? We know about that, but photons, as I told, qubits could be of the form photons too. So imagine that we have a vertically polarized photon. When you pass it through a vertical polarizer, it passes through. That wouldn't be any issue. But if you pass it through a horizontal polarizer, it is getting blocked. It is not going to pass. And in a similar way, if you pass a horizontally polarized photon, it will pass through a horizontal polarizer, but it will be blocked by a vertical polarizer. But when you use something like a 45-degree, polarizer, as shown in the picture, a random 50% of the photons would be passing through it, even if it's horizontally or vertically polarized. It won't be blocked off, but some amount of it will be passing through. So now this is called the BB84 protocol, which was introduced by one of the greatest pioneers in quantum computing field right now, Mr. Brassard and Mr. Bennett. So let's just say that there is a woman called Alice who wants to communicate with Bob through quantum communication, and you want this to be very secure. But there is another person called Eve who's trying to eavesdrop on what you guys are communicating. So generally in cryptography, what you do is you will have a set of information, you code it into something and you pass it, and a receiver receives your encoded encryption, and then you decode it using a key. And this key is something that both Alice and Bob, that's the sender and the receiver, would be sharing. So this is a kind of a shared key. So both of them would be having it. So generally, in encryptions, you do an exclusive OR. So we might have learned exclusive OR gates. So what does exclusive OR gate do is that when you have a 0 and 0 as your input, or you have 1 and 1 as an input, when you have 0 and 0 or 1 and 1, the output is 0. But you have 0 and 1 and 1 and 0, you will have the output as 1. So this is the kind of this is how the exclusive OR gate works. So generally, you will decode your information by exclusiving or by exclusive ORing the information with the key which you have. Sorry, exclusive ORing is something a little confusing. So I'll just explain it better. So let's just say Alice wants to send a message, Alice message, and Bob receives some kind of bits, but we don't know because it is not going to be meaningful. It's going to be in another way. So they both have a shared key. This is a key that Alice and Bob would be having. So something that is unique to exclusive ORing is that when you do exclusive OR once on a certain number of bits, and you do exclusive OR to the result again, you will get the original back. So that is what we are doing in this kind of encryption, where Alice decodes a message by exclusive ORing it with a shared key, and then Bob receives this encrypted code and decrypts it by using the shared key. And to make it even more secure, what they do is that this key is a single use key. You can use it only once, and it's going to be shared, and it's going to be random. It's not something that they're going to decide and then send. So I'll tell you why this is being done in such a way. So in this picture, we could see that let's just say, like, forget about the diagonal qubits. Let's assume that we have the rectilinear qubit format. So 1 and 0, and the polarization state is that vertical or horizontal. So Alice sends a set of bits, maybe 1 0 0 0 1 1 1 1 or anything, and through the quantum channel in an encrypted manner. So how does she encrypt it? By using a shared key. We still don't know what is the shared key. She picks something at random and sends it to Bob. And this is being done by an optical switch, which you can call it as a polarizing filter too, which would be polarizing everything. And then once Bob gets the photons, which are the qubits which are being received by Bob, he can again exclusive OR it and find out what it is. But the one issue over here is, if Eve is going to be there, Eve can receive whatever data that Alice is sending and make a polarizing filter. Let's just assume that she uses a vertical polarizer, and whenever the photon which she receives is being blocked, she would know that it is 0, and whenever it passes through, she would know that it is 1, and then she'll know the exact bits which Alice wanted to send to Bob. So she'll know the information, and then she'll generate the same information and send it to Bob. So Bob would never realize that this information was corrupted in between. So Eve would just get the information without even Alice and Bob realizing this had happened. So how do we solve this is we use another kind of polarization in the same system, which is what is depicted over here as diagonal polarization. So now Alice decides to use both kinds of polarization, which would be rectilinear as well as diagonal, and she doesn't know which is going to be what. She's going to pick something at random and sends it to Bob. Now Bob is going to detect these things, and obviously he'll get a set of outputs, which is being shown here. I hope this is visible. Bob's detected bit values, which is going to be 11011100 for the input 01011101. So I'm sorry, I'm going fast. So Alice uses a set of coding scheme, which is by, like for the first bit, you could see that she uses diagonal polarization. The next bit also she uses diagonal, but then she uses the light blue one, which is horizontal. So this is going to be random. So Bob doesn't know what it is going to be, but Bob receives this, and he also chooses a random set of, he chooses a random set of encoding scheme. He will choose rectilinear or diagonal for any bit, like it's his wish, or in a random choice, he's going to take it, and he's going to try to code whatever information that Alice sent to him. And in that way, he's going to receive some kind of output. It could be 0 or 1 or something. And you can ask for the first bit, you could see that Alice sends in a diagonal scheme, but Bob is using a rectilinear scheme. So how is Bob getting 1? So as I told, when the angle is changed, like from 90 to 45, at least like some amount, like 50% of the polarized photons passes through. So from that, he is getting the output 1. But we know over here that the right answers by using the right coding scheme is the ones which have been circled over here, the 1110. The remaining ones, irrespective of whether it was right or not, it was only because of he was using a different encoding scheme. You cannot be using it again. So this is through the quantum channel. And now if you see, they use another channel too, which is the classical channel. So classical channel would be something like your internet or phone or something like that. So Alice and Bob communicate through this, and Bob shares whatever he gets. So whatever kind of output he has, and he would know what kind of encoding scheme he has used to get this output. So then Alice receives whatever encoding scheme Bob used, and she knows now that whatever thing encoding scheme coincides with what Bob used. That is the encoding scheme used for the circled qubit states. So whatever are these encoding schemes, Alice will from now on use this as their shared secret. As you can see in the last line, Alice and Bob's shared key would be 1110. Even though they had a different key, this is going to be their shared key. So from now on, whenever they pass any different messages, it could be like hi, how are you, or something. The encryption key would be whatever they receive here. So now you can see that we are like polarized, like detecting in different ways. As Akshan's told, once you measure a photon or whatever it is in its quantum like state, we don't know what it was before the measurement, but once it is measured, it cannot go back to that state. The wave function collapses. So now with this result, they will be able to like securely communicate between each other. So this is some like a small start to like how quantum computing can be applied. So now moving on to like small applications and like how it actually works. So here we could see like a little math. So what it does is that it's all kind of quantum computing is represented through matrices in a mathematical realm. So for a bit, when you take one bit under consideration, you might have either 1 or 0. That's what we discussed before itself. So we use two rows. So you can see a 2 into 1 matrix, which is like one column and two rows, and each row represents the probability of that bit being in some kind of state, either 0 or 1, whatever it is. Like as Akshan told, spin, like spin, quantum spin could be like through its magnetic field where it spin up and spin down. It doesn't literally like spin up, but we just consider it to be like spin up and spin down, or like even in photons you can take it as horizontal and vertical polarization. So let us assume that we just call it spin up and spin down. So here the matrix is represented by the first row represents the probability that whatever bit you have is spinning down, and the second row states like holds the data about like probability of whatever qubit you have is spinning up. So for a qubit which is in spin down state or the zeroth state, it'll have a probability of 1 for its spin down state. That is why you could see for 1 in the first row and 0 in the second row. So this is something where it demonstrates deterministic behavior. You already know what is the probability. It's just one that it's going to be spinning down. In the beginning I told that you have superposition where it could be 0 and 1 at the same time, but here it would be either 0 or 1, only one of it. And then it's represented by, like if you see over here, there is one 0 with one arrow mark. It's called direct notation, where instead of just, like representing a full matrix and things like that, you just like represent it with a small notation. So I just tell here that for 0, for having the spin down state or off state as you would call in the classical computing, the matrix representation of that qubit is that it will have 1 in the first row and 0 in the second row. And what it means is that the probability of this qubit having spin down is 1. And hence, since this probability is 1, the other probability would obviously be 0. So we just like write 0 there. And similarly, for an on state or spin up state, you have a matrix which has 0 in the first row and 1 in the second row. And I again repeat myself that all these matrices are only probabilities. It's not like something else, but it just demonstrates, like it represents the probability of what the qubit is in, what state the qubit is in. So this is deterministic behavior where it's going to be up or down, one thing. And second, you have superposition. So how it differs is just that you will have different probabilities. You have 1 by root 2 in the first row, 1 by root 2 in the second row. So what it means is very simple. Just like when you take probabilities, you have to square whatever is represented in the matrix. So if you have 1 by root 2, square it, and 1 by root 2, square it. And if you add these two states, you get 0.5 plus 0.5, which is equal to 1. So the matrix represents the entire probabilities and for the qubit state. So the first, as I told, the first row represents the spin down and the second row represents the spin up. Here we have 1 by root 2 and 1 by root 2. So what it means is that qubit, that particular qubit whose matrix representation is this, has equal probabilities that it is going to be in the spin down state as well as the spin up state. Or if you want to talk in the classical computer terms, it's in the off as well as the on state. This is what is like, superposition. You can have it in both states at the same time, and we don't know anything unless we measure. Once we measure it, we'll fix it to one specific state or something like that. So it's represented in the direct notation by 1 by root 2 into ket 0 plus ket 1, which is very simple, just the representations which were used before. So I wouldn't take much time you doing math. It's just to show how the things are done or in quantum computing. So that what we discussed about till now was only for one qubit. So now let's take multiple qubit systems, and for making it basic, let's just have 2 qubits. And as I told before, the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And this is the probabilities of these are represented by the state vector, which I have written over here. And for example, let's just take that this multiple qubit system is going to have a probability of 0, 0. Both are going to be in the off state always. So that is being represented in the form 1, 0, 0, 0, where each row represents the corresponding combination of the qubits, either 0, 0 or 0, 1, 1, 0 or 1, 1. And when you just represent it in the ket notation, you're going to do it with a line and 0, 0 and the arrow mark or the greater than symbol. So why you do this is just to show that the probability of having something is only totally 1 for 0, 0, because as you see, remaining all combinations have 0 probability. You're going to just represent 0, 0. And the next example is a very different example. I'll talk about it. It's just 1 by root 2, 0, 0, and 1 by root 2. So what does this say? It just says that 0, 0 has 0.5 probability of happening, as well as 1, 1 has 0.5 probability of happening. And 0, 1 and 1, 0 cannot happen. The probability is just 0. And I've just represented it in ket notation. So why this thing is different is not only because it has multiple probabilities of superposition. This is also because of entanglement. As Aksan told, entanglement is where two different bits have are someday related to each other, which we don't know about. Even Einstein defined and called it as spooky action at a distance, because there is an instantaneous change in the characteristics of the other quantum particle, which is entangled with one particle when you change this thing. So why this represents entanglement is because the probability of being 0, 0 is 0.5. 0, 1 and 1, 0 both have 0, and having 1, 1 is 0.5 again. So the probability of having a 0, 0 affects the probability of having 1, 1 once you use it in some places. So this is called entanglement, where one quantum particle, let's just say qubit over here, influences the characteristic of another quantum particle. So this is a mathematical representation of entanglement. So I won't take much time doing math. This I'll just show one demonstration. So we all know that about gates, and gate, or gates, very simple ones. If you're in and gate, you have to have like 1, 1, like both should be 1 to have 1, and remaining is just 0. And for OR gate, if you have 0, 0 alone, it is 0. In the remaining cases, it's 1. And these kind of logic gates are the building blocks of your computer, because different transistors use different gates for different computations. Even for adding, like you can write code for just like 2 plus 5, but even for that result, it uses a lot of gates. And yeah, it uses in a very very short span of time, but still gates are being used. But that's not the case in quantum computing, because you're going to use a slightly different kind of um gates in this. So the NOT gate alone is the same over here. So the NOT gate is represented by the matrix 0, 1 and 1, 0. And I'll show what the drawing is about in a short span of time, in about 5 minutes. So when you mathematically apply a NOT gate over a bit, let's just say we take a spin down qubit, and you remember that the matrix was 1 and then 0. You just multiply it. It's just basic matrix multiplication. And you could see that the 0, 1, 1, 0 just transformed the qubit states. So now it is 0, 1, which is having like the spin up state. And another gate, like there are many gates, and I'll just cover a very few to demonstrate the gate working. Another gate is called Hadamard gate. The purpose of Hadamard gate is that when you have a qubit at 0 or 1 state, the Hadamard gate puts it into a superposition state. Like this matrix multiplied with spin down qubit completely changes its states and puts it into a superposition state, where you'll have different probabilities for different combinations, or whatever like superposition you're going to have, like for multiple qubits, if it's going to be say 1 qubit, 2 qubit, and so on. But over here, Hadamard gate is always applied onto 1 qubit. These gates over here are just 1 qubit gates. So next I'm showing a C0 gate. A C0 gate is something like an XOR gate, but it's slightly different. So until now we saw in this one, these were all a single qubit gates, and now we have a double qubit gate. So what does a C0 gate do? In like normal sense, it just influences another qubit. So like simply speaking, whatever X has, that value is going to influence whatever value Y has. So we might have heard about this, which is just the XOR gate, which we talked in cryptography and everything. So like whatever, if we have the qubit state of X as 1, Y is going to be whatever Y had initially, its not value. And similarly, if X is going to be 0, Y is just going to be Y. And the matrix representation is this. So to like think it like simply, you can just call it X or Y. So now I'll just show a small demonstration on how like quantum gates work. Just a second. Yeah. I hope the screen is visible. Yeah, okay. So now this is something that many companies are providing right now. We have big companies like Microsoft, IBM, who are like investing a lot into quantum computing and its research. So if you are a Windows user and you use Visual Studio for like programming and purposes like that, Microsoft has introduced a language called Q Sharp, which you will be using to program your quantum circuits or whatever it is. And you can like simulate whatever you want to achieve, and you can do this in Visual Studio. People who are interested can do that. And another one, what I'm showing here is IBM's quantum experience. It's free of free of cost, and it's something that is introduced for learning purposes. So you can experiment some gates, you can like try some codes in quantum computing, and like get the results. So what it does is like something like whatever input you're giving, it's going to be sent to a central quantum computer or a quantum simulator that IBM has, and they're going to like send a result of whatever you wanted. So I have one thing over here, this circuit which was designed. So what it is just that this is called a Bell state gate. As I told, like Hadamard gate, Hadamard and NOT gates are applied on one qubit alone, and there are two qubit gates, and then there is some gate called Toffoli gates, which is 3 qubit, and I don't want to go much into the details. So let's just see here what these qubits are. So first, the every line represents a, a qubit's timeline, like from the beginning, like just go from left to right. That is a qubit's timeline, and initially whatever the qubit is initialized to, you can see zero, right? Zero is the spin down state, and initially these qubits are in those values. So one very important concept in quantum computing is that you can never change or like reverse an initialization. So once you initialize a qubit to certain value, you cannot go back, and because you really don't know what it was before. As Akshan told, the wave function collapses. So after that, where do you reverse it? So you might think like, how do you make it 0 or 1, things like that? It is only through gates. So all these quantum gates will change the states of the qubits which you're using, and again when you measure it for your output, you can never reverse it. So you have irreversible initialization, then you have reversible gate operations, and then you again have irreversible measurements. So the only place where you do everything is the reversible gate operations. So what I have done here is like use 2 qubits, in which the first qubit is initialized to 0 or like spin down state, and I've applied the Hadamard gate. It's very simple. If you're interested, you can just go and create an account and try, and then you just have to drag the gates, like different gates represent are being represented over here. If you are interested, you can research more. So I put the Hadamard gate onto the first qubit, which is q of 0, and this is going to make the first qubit to be superposition. Like you will have different probabilities other than just having spin down state. And then what I have done is that placed a C naught gate. As I told, C naught is just like an XOR gate between two inputs, or like two outputs. So what I've done is like 0 and 1, I have placed a C naught gate. So whatever value the first qubit is going to have, that is going to influence the second qubit's value. And after that, the two things where you can see something like a measurement bar, or like whatever you would have seen in an ammeter or something, is your measurement symbol. So once you do this, you cannot reverse whatever you're going to have. So now what I'll do is I'll just run and show this, and I'll just tell what Bell state is quickly. Bell state is one of the simplest examples of entanglement. And why is that? Because you're changing, the superposition, the qubit state, and then you're influencing one qubit with another thing. So it's one of the basic examples of entanglement. So I just run this code, and they just ask you some details about how many times you want to do this for like statistical accuracy, because each time you're going to get a different output. So this circuit has been sent to a simulator right now, and then it's being calculated right now in a simulator somewhere, and just we are waiting for the result of whatever it's going to give. And yeah, the result is over here. So once I open it, uh, just a second. Yeah. So the result has come to us, like how much time it took and everything. And I just showed this thing. So this is the important part. If you can see the histogram, it shows us the probabilities of the states of the like both the qubits. So the first qubit has a probability of 49%, and the second one has around 50%. So what is this? This is something like superposition, right? So let's just say approximately you have 0.5 as the probability, because it's almost 50-50. And we could see by that, like by whatever computing we did over there, or whatever gate we created over there, like generally these kind of gates, when you draw in your books, like digital circuits, you will draw an AND gate and do this. But IBM is providing another facility where you can design these circuits and see, instead of just like writing codes and everything, you can just design, and for fun you can do it if you're interested. So now we have got the result, which has given the probabilities of the states of these qubits. So what we have done right now is just send something to a quantum computer somewhere to do something what we want, and we have actually manipulated some qubits. Like we have changed its states from just what, like it just looked like a drawing, right? Whatever I did, like placing qubits or like just like assembling something. That's how useful these kind of things are. So many top companies. I'll just stop sharing the screen right now. So many top companies like this are, like investing in quantum computing. Many countries are investing in quantum computing. And why is that? Because we are moving like quickly towards like, the future. Like imagine in 1960s, I personally have seen a lot of memes and Instagram saying like, just a few MBs hard disk would be that huge. And now even a 128 GB pen drive is just this small. So there are lots of advancements that keep coming in computing. And then there are some myths and some questions from people like, you know if quantum computers come, will classical computers just go away? No, that's not true, because your classical computer has to be used for many purposes. Like you cannot go and watch Netflix probably in a quantum computer, because quantum computer is specifically like going to be designed to solve problems in a very efficient and a very quick manner. Like let's just take a supercomputer today. It will be the size of two basketball courts. And if a quantum computer, which is also going to be large now, if you see today, like all Google's quantum computers would be like quite large. And that's nothing like, that's not like very weird or anything, because if you see the computers designed by Charles Babbage, it used to be very big. And then in 1950s, when the first, computers were used with vacuum tubes and punch cards, computers used to be like so huge. And now look at me, like I'm just having a computer to talk through, and then I'm just using a phone. And so we really don't know what's going to happen in the future. We don't know if quantum computer can be reliable in the future also, because there are a lot of issues. Like one big thing which you might be reading in the news would be that if quantum computers come, is that the end of privacy? Like everyone will be able to decode everything. Just I told like RSA algorithm can find things. It's exactly not like that, because like see, as much as development you make, as you like decode something, you can find something new also. And at the same time, another reason is because like to like efficiently decode something using a quantum computer in that speed, as I told, like if you decode something in a supercomputer, it will take thousands of years or something, and in a quantum computer it will take few days or something like that. You would need a lot of qubits, like thousands and millions of qubits also. But to make it to like reliably like depend upon the quantum going to decode it. But today, as of today, the number of qubits operating, like even the most powerful quantum computers have around 70 qubits or something like that, 72 qubits. I think that Google has it, 72 qubit computers. And then there are many companies which are investing in this, like D-Wave Systems, Google, IBM, Microsoft, and a lot of companies are like going through quantum computing, and a lot of countries are investing in this, because this might be the future. This might be the beginning of the future. This idea was started by as Akshan told, one of the most brilliant quantum physicists, Richard Feynman, and another mathematician, Yuri Manin. And then there were a lot of pioneers in the field, like Shor, Grover. Like many of them gave so many algorithms which could be implemented. And as I told now, the BB83 protocol, which was given by Mr. Brassard and Mr. Bennett, they are still working in this field. So constant updates are being done. So like for a quantum computer to be efficient, it will take a lot of time to be actually coming. So why? So it will take a lot of time, but then we have to have this constant research, and we have to dedicate ourselves to find a lot of new things. And see, we never knew that quantum physics would actually be showing a new kind of computing itself. So like it's just magic, I would say. If like imagine whatever we learned from our childhood is just that you'll have an on or off. If I myself in my childhood would try to balance the switch between on and off, and I really didn't know how it works or anything. But then now and then now as I'm growing, it's just that we get a lot more ideas. I never knew about quantum computers like few years back, or how they work. And before that, all I thought about was just on and off. All we learned in school was just on and off, on and off, on and off, just two possibilities. And people who watch Dark might also know that they'll talk about on, off, good, evil, and those kind of things. Just bringing dark because of the quantum, physics, which involves a lot over there. But then the new condition which we saw here was like few things like superposition and entanglement, which we don't know the reason for. Like, being in the same state at the same time, like one or zero, we really don't know what it is, one or zero. And at the same time, entanglement, like one bit, like influencing another bit. And just imagine whatever this is, we are observing it in a quantum realm. So we really can't see it physically. But if we see it physically, we would obviously accept that this is magic because we really don't know what it is going to happen if it's going to be in a macroscopic level. So this kind of new innovations and new research and new systems are only towards progress. And as we progress, we'll find new problems and new solutions for the problems, and those solutions might find new problems, and it just keeps going on. So these kind of things are just like some of the biggest mysteries which are in human history and which are going to come. And these things really need some kind of innovation as well as dedication and interest from human beings to be put in to research and progress more. And as I told, it's a very useful thing. Like quantum computers can help you simulate a lot of things. It can help you simulate the quantum world itself, which would answer a lot of unanswered questions which we have today. So quantum computing and quantum physics, though they might be a little different topics, because quantum physics is like the parent, it has a lot of topics. We just covered one application of it as quantum computing. So now I'll just like say that Akshant would like to say something before I would end this thing.
No,
Yeah.
nothing. Just that I like the way you explained that. That was very informative. And to all of those who are watching and will watch this in the future, this is like it's a stepping stone to start learning about this, something new, because it's just fascinating stuff. And my mind is blown. Tirtha is very smart. Okay, that's all I have to say.
Yeah. So if anyone are interested to talk more about this or anything, you can contact us. We are really interested in these kind of topics. So and I just hope that some kind of curiosity has been put into you. I started like trying out these quantum circuits just because it felt new to me. And if some kind of interest has sparked inside you about quantum physics or quantum computing or anything in that domain, that would be like a really good moment for both of us, that it has helped us to influence in some way or like show some ideas. That's it. So yeah, thank you.
Yeah, thank you.
Thank you guys. Bye bye.
Bye.